I'm just looking at the resolution here. Does it look right to me? That looks okay. Okay, so I got a question right before the class. How is all this crazy math stuff? Have we started on pre and post conditions?
Yes.
Okay. So the question. Okay. So the question is, why do we have to deal with all this math stuff when all we want to do is to become better programmers and better at debugging programs or writing better programs to begin with? Okay. So I want to show you a picture of what happens when your program stops working or when it has a bug or has some kind of symptoms. Okay. If you think about the timeline of your program executes, and at some point, right here, the symptom becomes observable. Okay? There is a distinction between a bug, where a bug is, and where the bug becomes observable. Is that okay? So this is the first time that you can observe something. The bug becomes observable. Okay, there's a symptom that you can actually see. Maybe the screen has the wrong output. The number is wrong that you can tell. A button is, an LED is lit up. The default LED is lit, and so on and so forth. But at some point of time, something is observable, and you say, "Uh-oh, the program is not working the way it is supposed to." Okay. Now the question is, where is the bug? Where is the fault in the program that causes this to happen? What are the chances that the bug is right here? Almost zero. Okay? So you're talking about a bug or a fault in software, a mistake that the programmer has made that has happened somewhere before we get to the observable point. Right? The question is, but how do I know where along this entire timeline the bug is actually located? What do you think? First of all, when we have the observable symptom, it would be nice if we can understand exactly which line is producing this observable symptom. And that's usually not a problem. Okay, any good debugging environment will probably give you a line number and say, okay, line so and so is causing the crash. So you know exactly when the program actually stops working. But the bug can be somewhere up here. It can be down here, it can be all the way up here. We do not know. All right? So what we need to do is to start with this. Okay? Let's just say that at this point here, you are lucky enough to run a debugger, and you can actually say, tell the values of all the variables at this point. Sometimes that is not even possible, but let's just say it is possible. Okay, the state of all the variables are now known at this point. Okay, and since you already know the line number, okay, so you have your program. Line numbers here, and then you have your code here. So we know the problem is occurring on this line. This is where the observable symptom occurs with this line here. Can we go back in time and try to figure out at which point the problem actually happens? We can try, at least. Okay? Because what we can do is we can say, in order to get here, we have to get here first. Okay? Is that okay? I know the entire state of all the variables at this point. Can I go back and say, before this statement, the variables must be in this state the line before? Sometimes yes, sometimes no. But we hope that we can do that. So using this method, we can try to move back in time, looking at the source code or the algorithm, and see, okay, we can check everything. If I get to this line, and we get this output, everything is good. If I got to this line before and the state of the variables are like this, everything is good. And then you keep going this here until you get to a point where it does not make any sense. I really should not be here. That is the wrong branch. Okay, that is the faulty code. In other words, we want to go back in time and be able to tell as much as we can what is the condition when we get back to this point. Because if you don't know the condition at that point, then you cannot debug the code because you cannot understand why you made a decision to go here instead of the other side, which probably is the right branch. Okay? So now, understanding this, let's go and take a look at how we can apply what we have learned so far. Have we talked about the inverse function stuff in this class? Okay, so that's very good. So let's just say that we have a mysterious line 43. Okay, line 43 is already known because I have access to the source code, and the source code says x gets x divided by 2. Let's just say that we are talking about integer division here, so everything is done by integer math. And this time, I'm not going to tell you the precondition. I'm telling you the postcondition. In other words, the program somehow crashed after line 43. I know something is not right. Okay, and I know what is post 43 because the debugger tells me about the values of the variables and so on and so forth. Let's make it very simple. Let's say that at line 43, we know that the variable x has a value of, well, I don't care, 11. Can I go back in time and tell what is the condition, what is pre-43? Exactly. Does that have anything to do with the inverse function thing? It has everything to do with the inverse function thing. I mean, you can figure this out pretty intuitively because we have a very simple condition, and the operation on the right-hand side of the assignment statement is also very simple. But the principle of being able to reverse the operation to go from a post condition back to a precondition is basically the application of what we have learned so far regarding the function and the inverse function. Okay. Now there will be points where you will hit you will basically go. You can trace back up to a certain point, but there are points where beyond this point you cannot go anymore. Okay. Because it is an assignment of x equals 0 or something like that. So there's no way for you to track the value of the variable before this point. It's not reversible anymore. Okay? So at some point you have to design experiments and say, okay, we'll just try different test cases with this program. We know this test case will cause the program to bomb. But will this test case, which is very similar to the other one, also cause the program to bomb? Okay, this one does not cause the program to bomb. This one does cause the program to bomb. Then you have to go forward again and use logic to try to differentiate how come this test case is going to bomb the same way as the other one, whereas this one is going to work just fine. Okay, but the ability to move forward and backwards in your code using just mathematics is very important. So is that question answered?
No.
No?
Because using your logic, you can always go forward or backward using that function.
Not always, because when you have constant assignments, then you will hit a dead end.
Okay.
Yep. So there are always limitations as to how far you can work your way back, knowing that the program crashed at a certain point. Okay, but the ability to go back in time is also very useful.
Oh yeah.
Yep.
That only works if the right-hand side refers to the left-hand side, right?
Correct. Because if your right-hand side is, say, a constant like 0, 5, or whatever, then there's no way to reverse that operation to go any further. Yep. On the other hand, just because you can no longer track that one variable doesn't mean that you will lose everything that you know about the other variables. Okay, because let's say you have 10 variables at a time that it crashed. As you work your way back, you may lose 1, 2, 3 variables as you work your way back, but you will still have all the other variables that have not encountered a constant assignment statement, and you can still use those to try to go back, to try to track down where you might have made the wrong decision in a branch or a loop or something along that line. the idea is to try to push back as much as you can. Once you get to a point where you can no longer push back and say, okay, I know I have to be at this point, I have to get past this point for the symptom to show up, but I don't know how I got to this point, then you have to look back and say, okay, what are the different ways for me to get to this point? Because with most programs, there are multiple ways to get to a certain point. Then you have to look at what are the alternatives? How can I get to this point from multiple vectors? And then you have to design experiments to test each path and say, okay, did I get here because of this? Did I get here because of this? Did I get here because of this? And that part is mostly heuristic. It's based on experience. Because which way do you try first depends on how many of these problems you have encountered, and intuitively, which one do you think is the more likely cause of the problem? So a part of that depends on experience as well. How well you can debug a program depends on experience. Okay, any questions so far? Have we talked about the mechanical methods of applying the substitution method? No? Okay, let's go ahead and do that instead. Okay, or start with that. So what we want to do is to give you an example. Well, 943 is a good example, just like that. So this time we're not reversing from post back to pre, we're going from pre-condition to post-condition again. So I will just say that it is given, I'll just write down here, it is given that pre-43 is x is greater than z and y does not equal to k. That's all we know before line 43 executes. Okay? Any questions at this point? So the next thing I want to do is to show you mechanical steps that you can go through in order to figure out the post condition. So I'm not going to do this on a case-by-case basis. We want to figure out a way where we can do this very, very mechanically. So I will divide it into steps. Step 1, pretty easy. Okay. The question is, does the right-hand side refer to the left-hand side? In other words, if you look at the right-hand side of the assignment statement as an expression, does it refer to the variable on the left-hand side? That's the first question. Okay? So I will say if the answer is yes, go to step 2. Else, go to some other step. We'll fill that in later.
I don't think there is a chair.
There's a.
Well, we have these.
That will work.
You have to figure out a spot. Sit down. Okay, so we'll figure out the dots later. In this particular case, can we go to step 2? Okay,
Yes.
we can go to step 2 because the right-hand side does refer to the right-hand side refers to the left-hand side. Okay, so you basically want to call the right-hand side a particular function. Did I explain what a function is? I think I did that because you need that in order to understand what is an inverse function. So call the right-hand side a function. So in this case, I will call f of x to be x divided by 2. Is that okay so far? Okay. Step 3, try to find an inverse function f prime of x. Now, just because function x or f of x refers to x does not mean there is an inverse function. Okay, that is not automatic. In this case, yes, we do have an inverse function. How do you reverse the operation of dividing something by 2?
Multiply.
You double. You multiply it by 2, that cancels out the division by 2. Okay? If an inverse exists